We're here at Midwestern State University, McCoy Engineering Hall. This is our energy system laboratory, or heat transfer. Let's go in here and kind of take a quick look. First, our safety, we have a fire extinguisher, first aid kit, and a eye wash station. I will now introduce Dr. El-Sharafi, and he'll talk about the heat transfer class.
Yeah, hi, how are you? Actually, heat transfer class is designed to let the student know about how to measure the conductivity and also how to measure the resistivity and how to calculate the convection and the radiations, and also to study, the inverse square law by using rotometer, to measure the R, and then we get a draw between the distance with radiations. And also another experiment, which we used that to measure, the pressure, the temperature distribution along the bin cylinders. First, let me start with the first experiment, which is the thermal conductivity of the brass cylinder. In this one, we have to insert the brass cylinder, which is gonna be in the middle. It's gonna be in the middle there. It's already there. That's a brass. The brass metal. And then we have to apply voltage, which provide the heat from the power supply, and this voltage will provide a flow rate of heat transfer. It's going to flow from the top. We have some thermocouples, connected to measure the temperatures, around the brass samples. And then we're going to circulate the cold water, and the heat transfer will be between the source of the voltage, it's provide heat, and then we provide the cold from the bottom. And that's, the student, they have to do some of the calculations, and they have to calculate, different parameters regarding to this experiment. Then, second experiment, we're gonna, instead of the brass, we're gonna use different materials, and that's the second experiment, which we call, aluminum, stainless steel sticks in the cylinder without thermocouple 4 and 5. We will not use thermocouple 4 and 5, but we use the thermocouples 1, 2, 3, and 6, 7, and 8. And those connected, to the power supply. And the student, they have to measure the conductivity, according to the materials, because we're going to use two different materials. And they have to compare, like, the conductivity for the stainless steel, for the aluminum, and also for the brass. And of course we know the dimensions of those samples. Another experiment also, it's done by using this device, which we call H1 112A, a linear heat conduction system. And then we use the cork. A cork is a piece of wood, Of course, the resistivity of the cork is very high, and the student, they have to measure the resistivity instead of the conductivity for that. That's the third experiment. Another experiment, the student, they have to do again, with the brass, and that's, we're gonna measure, like, the temperatures 4 and 5, which is above and below the brass itself, right now, because we have thermocouples, 4 and 5 for this. Okay, another experiment, which we call it, the conductivity for the thick wall cylinder. And here we have a cylinder, and the student, we have a cylinder is inserted, in this, this device here. Which is, the student, they have to measure the conductivity of the thick cylinders. It's similar to the previous one with the different, dimensions. Let me go to the experiment I think it's experiment number 5 or 6 here. Yeah, because we have you know a similar experiment that we're gonna do with this machines here. It's about the radiations and convection measurement, and this is, we call it determinations of the combined radiation and the conventional heat transfer coefficient without van blower. Van, we will not use it van here. We have a butterfly valve here. The van, it is not used for the air velocity here, because we have, you know, static measurement for the radiation and the convection right now. And we apply, you know, a voltage to provide the heat. We have the cylinder, and then we measure the temperatures, you know, distributions around the cylinder, and then, you know, we have to calculate and find out the coefficient factor for the radiation and the coefficient factor for the convection. And as I said, first experiment, that's without velocity. We don't have the air is moved. Second experiment is going to be the same with this machine, and we're going to use the velocity. We're going to turn the air pump. We're going to turn it on, and then we start having air flow through around the heat transfer, and around the heat transfer, because we have a cylinder, you know, around the the hot surface, and then we measure the radiation and the conventions coefficient factor using, you know, a different speed of air. Another experiment here, which is it used to for the radiation error and the temperature measurement. Radiation error and the temperature measurement. For this experiment, we have used a shield. It's on the head, as you can see here. And one experiment is without shield, another experiment with shield. And we have a ceramic here. It's connected to the power supply. We use a different voltage to apply, you know, the heat on the ceramic, and then we're gonna measure, you know, the same thing, the convection and the radiations, you know, by you know different speed, and we need to compare this result with and without installing shield on the head of the cylinder. And of course, we have the butterfly valve. This is used for controlling, you know, the speed of the air. Another experiment, which is, we should have a rotometer here, and the rotometer, I think we have it, but in the it's on the shelf there, and we should have the rotometer installed here. That's the source of the heat. We apply the source of the heat, then we're gonna have a radiations, you know, rotometers. It should be here. It's gonna absorb the signal from the heat, and then finally, you know, we're gonna use a different distance. You know, we're gonna start with 100, and we go until 900 millimeter, and we have to make a relationship between distance and, you know, the radiation. We should have the curve for log of RC and log of X. The distance should be close to 2. That's why we call it inverse law. Another one here, that's a pin, and this pin has, you know, those connections here. Those give a signal like a thermocouple to measure, you know, the temperature distributions around the pin, and we apply, you know, voltage, you know, to provide the heat, you know, and then we have to study like the temperature distributions with the experiment, and also we have to compare our result that we got in the experiment with the calculations result. If the student did a very good job, their result should be close to each other. I think by this I'm gonna finish, and thank you so much, and enjoy the video.